Using these miniatures here, I'm going to demonstrate how a quicksort works. Now this is a more complex algorithm. The implementation of it in code is usually done via a programming method called recursion or recursive programming, where a function will continually call itself until it meets an exit condition, in which case the functions that are being called will return a value and it will kind of unwind back up the recursion pathway. It is a complex programming construct to understand and wrap your head around, especially when you get large amounts of data and you're having recursions that go down very, very, very deep. To unwind them is quite complex. So I'm not going to talk about recursion any further than that. In terms of some of the programming constructs you'll look at: repetition, iteration, very similar, sequential instructions, conditional instructions or selection instructions. Recursion is one of those, but it's not one that you're going to need to cover. Anyway, on with the selection sort. Quicksort. So what I need to do, I've got a line of miniature models here, and I want to sort them from smallest to largest, with the smallest being on the right here, the largest being on the left. What I'm going to do is to select at random or semi-random, assuming that the list had a lot of data in it. I just pick the middle one. And this is going to be my pivot point. Anything that's smaller than this is going to go on the right. Anything that's larger than this is going to go on the left. There's quite a few comparisons in this, but as you get larger amounts of data, the need for sorting becomes less and less and less, and it tends to sort itself, and then it kind of all comes together in the end. So what I'm going to be doing is not so much sorting, but just kind of saying, well, this is bigger, just chuck it on the right, this is smaller, chuck it on the left. And it will eventually sort itself out. So what I need to do is compare things, and there's no particular order to this. This miniature is clearly smaller. I'm going to put him on the right, and I'll make some space for them. The dog is smaller. I'm going to put him on the right. This guy is much bigger. I'm going to put him on the left. This guy is much smaller. I'm going to put him on the right. The dragon is bigger. He'll stay on the left. The little goblin archer is smaller. He'll stay on the right. The spider is smaller. He'll stay on the right. I still need to compare all of them, but I've done that, and now this part, this pivot here is done. It's in the right place. Everything to the left of it is bigger than it. Everything to the right of it is bigger than it. Everything to the left is smaller. So now with my new sublists, this here and this here, I'm going to perform the same task. So these two are going to have pivot points. And what I'm going to do is compare. Once again, everything bigger is going to go on the right. Everything smaller is going to go on the left, with this one as well. So this one here, it is hard to see. I think it's a water elemental, is smaller than the goblin, at least in vertical size. So he's going to go on his left. The dragon is bigger. He's going to go on his right. Down here, the spider is smaller. He's going to go on the left. The goblin archer is smaller. He's going to go on the left, and they might be out of the picture just for the moment. I'll bring them back in a sec. The dog is smaller. He's going to go on the left. This wizardy guy is bigger. He's going to go on the right. Now these three pivot points are in place. I don't need to do anything with them anymore. Now what I do, and you'll see what I mean by recursion a little bit here, is that the first time I had one pivot point. The second time I had 2 pivot points. The third time I'm going to have 4 pivot points. I'm just going to keep them back a little bit. Now with each of these pivot points, once again they do the same thing. This dragon is going to check and put everything bigger on his right, everything smaller on his left. There is nothing. That's considered sorted, and it's done. It's in the right place. Same with this water elemental. Everything bigger on this side, everything smaller on this side. There is nothing to check. It's done. I don't need to check the pivot points. We already know that they're in place. Then this guy here, the elementalist, there is nothing for him to check, so he's in place. Lastly, we have the spider. and everything bigger goes on this side, and this goblin archer is taller than him. Everything smaller on the right. There's nothing smaller than him. He's in place. Finally, I've got only two things left that I could be considered a pivot point, because there's nothing further along here, or one thing left that could be considered a pivot point. So I chuck it on either one of these. I could just do it randomly. And then I say everything smaller than the dog goes this side. Everything bigger than the dog goes that side. The goblin archer is smaller than the dog. He stays on that side. This guy's in place. Finally, there's only one pivot point left. There's nothing to compare it to, so he's in place. That's how a quicksort works. It works on pivots. I didn't really have to find where everything went in the list. All I did was sort one item in the list and say everything that's bigger go on that side, everything smaller on that side. Then I did it again and again and again and again, and each time the problem got smaller until there was only one thing left in the list, or one thing left in each little sub-problem, and then the problem was solved. So that is a quicksort algorithm. You'll notice with all of them, I don't actually need to check. There's no part of the algorithm that says, is the list sorted? And if it is, then stop checking. We just assume that if the algorithm is working correctly, then when we are done, the data will be sorted. There are tests, of course, that you can run on it. These tests would need to be done in a computer program, and you would check to make sure that every element in the list is either greater than the one before it. And those would be done once, or not once, but the tests themselves would be done before the program is implemented in whatever application it was going to be used in, to make sure that your sorting algorithm was working. But once it's tested and it's working correctly, it's not like you're going to need to run those over and over again. A test like that, comparing to make sure that this is greater than this, is greater than this, is greater than this, is greater than this, etc., would take a little bit of time to run. It would essentially be a linear search, checking that each element is greater than the previous one. With 7 pieces of data, or 8 pieces, or 9 pieces that I've got here, it's not going to take a lot of time for a computer program to check that. With 9 million or 900 million pieces of data that it has to check, it might take hours or days. But a test like that is still essential to make sure that the implementation of the algorithm is working correctly. Because if you need that information sorted and it needs to be accurate, which it does, then testing it is very, very important to make sure that whatever you're doing with it later, say you're going to be searching through that data, then if it's not sorted properly, you may not find something that you should have been able to find. So testing algorithms, testing computer programs is very, very important. Do not underestimate it. I'm going to look at a linear search next, and also a binary search.